Hello YouTube, DeVore here again, and today we are tackling the third exercise in Module 1 of Math 3. It's called Tracking the Tortoise. Now this is a continuation of an activity that actually came from the Math 2 textbook in the same Mathematics Vision Project series of textbooks, also from Module 1. The idea in Math 2 was looking at the difference in the rate of change between exponential and quadratic functions. But the focus of this one is actually to look more at how we deal with inverse functions when we have exponentials. In 1.2 and 1.1, we looked at linear and quadratic functions, and exponentials is the other ones that we've been working so far in this textbook. So let's see, you remember a task from last year about the famous race between the tortoise and the hare, and slow and steady wins the race and all that. So let's look at some of our starting values here. In the original task, one of the big things they were doing was graphing the way the tortoise moved and the way the hare moved. We're going to focus more on the tortoise. Here's our distance formula here. So distance equals 2 to the t power, distance being in meters, time being in seconds. So t being in seconds. The tortoise family decides to watch the race from the sidelines so they can see their darling tortoise sister Shelley prove the value of persistence. Okay, so our first question is, how far away from the starting line must the family be to be located in the right place for Shelley to run by 10 seconds after the beginning of the race? Well, all we really need to do here is plug in our time in here. So d of 10 is 2 to the 10th power, which should be 1024, I believe. Let me double check my numbers here. Should be 1024 though. When I'm not knocking everything over on my desk, it's awesome. Yes, 1024 meters. So roughly a kilometer in 10 seconds. That's actually pretty darn fast. Okay, then we have after 20 seconds, d to the 20th equals 2 to the 20th, which that is a calculator problem. When I plugged it into my calculator, I got 1,048,576 meters. That's a really long way. It only took them 20 seconds. Yeah, I think that this particular tortoise has broken the speed of sound at some point during its journey. All right.
Jill Stewart, 1001. Jill, 1.
Question 2 asks us about the graph of d of t. Now, it's asking about the important features. Just as a reminder, when we're graphing this guy, it's going to look something like that. And it's going to go up really quickly. So let's do domain and range first. In the context of our problem, we are assuming that our time starts at time 0. And we don't know how long the race goes, so we're just going to have it go out to infinity. For the range, well, one way to find the minimum part of the range is you look at kind of the smallest value that you have for your domain, and you go ahead and plug it into your original function. T to the 0 power is always 1. So starts 1, it actually says also in the problem that she gets a 1 meter head start. And again, we don't know how long this race is going to go, so we're just going to hedge our bets here and say it goes to infinity. Now there is a minimum value in the context of our problem, and that is our starting value. At time 0 goes 1 meter. There is no maximum value, again, because we don't really know how far this race goes. And also, if we look kind of at our sketch of the graph here, as we're going from left to right, as time is increasing, our distance is always going up. So we would write that that is always increasing. And that makes sense. I mean, it wouldn't make much sense if in the course of the race they were backtracking or anything like that. We're just assuming that's a straight shot here. Let's look at the next problem here. If the tortoise family plans to watch the race at 64 meters away from Shelley's starting point, how long will they have to wait to see Shelley run past? Well, remember, as a reminder, we have d to the t equals 2 to the t power. This time we know the distance, but we don't know the time. But we can actually find what our time is based on what we know. We have 2 to the t power equals 64. I prefer to count powers of 2 on my fingers, and I know that some people don't like doing that, but this is actually something I learned in engineering, that you work in powers of 2 long enough that you just start counting them on your fingers. So we've got 2 to the first power is 2, 4, 8, 16, 32, and then we add one more for 64. So that means t is 6. So if we were to plug 6 in here, we would get 2 to the 6th power, which is 64. How long must they wait to see Shelley run by if they stand 1,024 meters away from her starting position? Or in function notation, it's 2 to the t power equals 1,024 meters. We figured this out on the previous page. We know that at 10 seconds, she will have gone 1,024 meters. So there's using some math that we did before. All right, so now we're going to sketch a graph that shows how long the tortoise family will wait to see Shelley run by at a given location from her starting point. Now, basically we're looking at the way I'm reading this is that the how long, the time is our x, and the given location is our y. Maybe? Well, we'll graph it like this. Actually, no, looking at our previous questions, this is backwards. Okay. So we want to know at our input is distance, our output is time. Now, if you look at our distances, the ones that came out with the best numbers are powers of 2. So let's start just putting in some powers of 2 here. We've got 1, 2, 4, 8. We'll go out to 16. Now, since these are powers of 2, I'm thinking what 2 to the what power will give me 1. In this case, I know it's 0, 1, 2, 3, and 4. Now, I picked these numbers. I could have picked really any number in between here, but I really didn't want to have to deal with decimals. And that's just personal preference. So we've got 1, 2, 3, 4, 5. So there's 16 there, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 16 here. So let's just go 1, 0. So it actually is here. Wow, must be a Monday. I'm not doing very well today. 2, 1. 1, 2, 3, 4, 2. And then 1, 2, 3, 4, 5, 6, 7, 8, 3. Let's see, 8, 9. Oh, here's 16. 16, 4. So we can kind of start sketching the curve right through here. And it just continues on and on and on. So here's our question. How long must the family wait to see Shelley run by if they stand 220 meters away from her starting position? Well, we can figure this out. You know, we can start out by using our graph, but our graph doesn't actually go all the way out to 220 meters. What we can actually do is we can guesstimate about how, maybe down to the whole second or in between 2 different times of about how long they're going to have to wait. So once again, so we know it's going to be less than 10 and greater than 6, because 6 seconds is 64 meters, 10 seconds is 1,024 meters, so it's not near that long. So if we think, okay, we're counting again, 6 is 64, 7 is 128, 8 is 256. So 2 to the 7th equals 128, 2 to the 8th equals 256. Now if we want to go 220 meters, we know that she's probably going to have to wait sometime between 7 and 8 seconds in order for them to be able to see her. Now here's a quick gut check. If I know 128 and 256 are my two big numbers that I'm in between, which one do I think it's going to be closer to? 7 seconds or 8 seconds? Looking at 220, I'd say it's a lot closer to 256. So it's going to be closer to 8 seconds. Now, I actually went ahead and did the math on this one, and she would have to wait exactly 7.78 seconds. So there's the actual math. And this is a skill that we're going to be using a lot more as we go into Module 2, is being able to do this kind of a gut check on which ones are probably going to be closer to. Okay. What is the relationship between d of t and the graph that you have just drawn? How did you use d of t to draw the graph in number 5? Well, if you remember, I knew that in order for me to get nice numbers, I needed to use powers of 2. That came from my original function. And if we were to actually look at the table, now let me pull down the table here. If we were to actually look at this table and compare it to our original function, these would be our inputs and these would be our outputs, which remember that when we flip our inputs and our outputs, they are called inverse functions. So they are inverse functions. Woohoo! Something we've been talking about for the last couple of tasks. And remember that the way that I used d of t to draw this graph was that it told me what kinds of inputs would give me nice outputs, since I knew I needed powers of 2 anyway. All right, almost done here. Got one more page left on this task. Okay. Consider the function f of x equals 2 to the x power. Now, this looks very similar to our original function of Shelley the tortoise, but it's different because we are now no longer constrained by time. We can use really whatever kinds of x we want. The domain will change here. So the domain is going to be negative infinity to positive infinity. Now, in our original context, we had it start at 0 because negative time doesn't really make much sense. Here we have no such constraints, so we can go ahead and have negative numbers. And the range is from 0 to positive infinity. Now, you may ask yourself, why this 0? Why didn't it go all the way to negative infinity? And it comes from what this graph looks like. So if I were to draw the graph, and I really only need the top part, if I were to draw the whole graph, it actually kind of looks like that. See how it hugs that 0? It's never actually going to touch, and that comes from how exponents work. So if we were to go numbers, for instance, we have 2 to the 0 equals 1, 2 to the negative 1 equals 1/2, 2 to the negative second equals 1/4. You notice that the fraction is just getting smaller and smaller and smaller. I mean, here's an extreme example. 2 to the negative 100th power is 1 over 2 to the 100th power. That, that's a tiny, tiny, tiny number. And for our purposes, I mean, that's essentially 0. It's not actually 0, though. It's just a really, really small decimal. As this number gets more and more negative, this fraction is going to get smaller and smaller. And it's going to be approaching 0, but it's never actually going to touch it. That's why the range goes from 0 to positive infinity. The other question that we have is this function invertible? And remember that when we're talking about things being invertible, we want to make sure that if I were to invert this function, that it would still be a function? And the answer is it is actually invertible. It is invertible. Okay, so now we're going to graph the original function and the inverse function. And we're going to use the work that we did on the original just for ease here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here's 16 again. We're just going to go up to 16 on both the up and the down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So let's go ahead and start graphing. I'm going to graph f of x first. So I start out at 0, 1, 1, 2, 2, 4, or yeah, 2, 4, 3, 1, 8, and then 4, 16. And we can go up further, but we're going to quickly run out of room. So let's, uh-oh, come on pen, don't run out of ink on me now. So there's f of x right here. I'm going to just label the beginning of it. Now remember that for the inverse, we can just take what our coordinates are, and we're going to flip them. So instead of 0, 1, it's going to be 1, 0, 2, 1, and 4, 2, or 1, 2, 3, and then see it goes 4, 6, 4, 16, no, 16, 4, 16, 4. It's gonna look something like that. There is our new function, and the domain and range is actually pretty simple to find, because remember that if we flip the inputs and the outputs, we say that the domain of our inverse is the same as our range, which means it's going to go from 0 to positive infinity. So what's going to end up happening is if I were to extend this graph, it would kind of start hugging the y-axis. It's kind of cool looking. And then for the range, it goes from negative infinity to positive infinity. All right. Here's some last little questions here, just going off the definition of inverse. We have, if f of 3 equals 8, what is inverse f of 8? Well, we can go back actually to our original function here. It should be that we're basically asking ourselves here, what power do I need to take 2 to in order to get 8? That means f of negative 1, we count on our fingers here, 1, 2, see, yeah, 1, it's going to be 3. I don't know where my brain is today. Sorry, it was a rough night last night. I'm still kind of working on my coffee. We know this because they are inverse functions. All right, now we've got f of 1/2 equals 1.414. Now this number is kind of a cool number. This is the square root of 2. Just very much abridged here. By our same token here, if we were to put 1.414 into our inverse function, like this, we would get 1/2 back. And the answer, once again, is that we are dealing with inverse functions. Inverse functions are very powerful because sometimes we only know the output and we need to get the input. That's really what inverse functions are for. The world is a little more complicated than we'd like to think. Inverse functions help. Okay, last question here. If f of a equals b, what is inverse f of b? Now, by definition, it's going to be a again. And will our answer change if f of x is a different function? F of x must be invertible, but the definition is the same. All Alright, we made it through that task. Definitely, that was a little tougher than some of the other ones we've done. Hopefully the next one will go a little bit better. I like the next one. 1.4 is a lot of fun. So thank you for joining me in 1.3. As a reminder, this task is called Tracking the Tortoise out of the Mathematics Vision Project Math 3 textbook. If you like what you see, please remember to like and subscribe. And if you have any questions, please feel free to shoot me an email and I'll answer them as best I can. So hope you have a good day. Bye-bye.